Hi everyone, thank you so much for coming to this video. So today we're going to be going over double angle formulae. So it'll be really useful if you review the lessons that we've already done on trigonometry and their identities, because that will come into really handy for this video. So the learning objective for today is to be able to understand and use double angle formulae and their geometrical proofs. So we're going to be going over the theory and then also some practice questions just to make sure you fully understand everything. So like always, there's going to be timestamps in the description of the video, so feel free to skip to any parts you want to. But let's get started. So in order to work out what the double angle formulae are, so this is just what sine 2a is, what cos 2a is, and what tan 2a is. In order to do that, we need to use these addition formulae here, and then I'll take you through how to get your double angular formulae through this. But firstly, it's important to understand all of these and know where they come from. And we need to know the geometrical proofs of them. So the first one we have is sine A plus or minus B is equal to sine A cos B plus or minus cos A sine B. So I've written out the proof here, and I'll take you through it step by step. So we know that for sine, the double angular formula is sine x plus y is equal to sine x cos y plus cos x sine y. So in order to demonstrate this and prove this geometrically, you do this by stacking two right angle triangles on top of each other. So we have one triangle here, triangle ACD, and we have another, and side AD is 1. So let me just write that on just to make it clearer. And we have triangle ABC as well, ABC. And then we also have another triangle here, which is AFD, like inside, like that. And the side FD is opposite to angles X and Y. So if with the triangle AFD, if I do it like here, AFD, we have FD, we want to find that length, and we know that AD is 1, and this angle here is just X plus Y. So then if you remember, sine of an angle is just what the opposite over the hypotenuse. So our opposite is just DF, and then our hypotenuse is just 1. So we would have sine X plus Y, that's just equal to DF over 1, which is just DF here. So then we can also rewrite the length DF in terms of D to E and E to F. So they've just said that DF is just the same as DE plus EF. So then we want to write EF and CB. So we have the line EF, that's just the same as line CB because it's a rectangle. So that means those two are equal. So then we can rewrite this again by saying that sine X plus Y is equal to DE plus CB. So now we want to establish some of the unknown lengths of the size of the polygon. So if we work with what sine X would be, so remember that's using the triangle ACD. So we want to say that sine X is equal to the opposite over the hypotenuse. So your opposite length would just be CD here. Remember that's the length that's right angle to your adjacent, and your hypotenuse is just AD, and that's just 1. So that means that your sine X is just equal to opposite over hypotenuse CD over 1, which is just CD. And similarly, we know that AC here can also be written as cos X is equal to adjacent, which is AC, over the hypotenuse, which is 1. So that means that AC, which means that cos X is just equal to AC over 1. That means AC is equal to cos X. So we can use this to establish the length CB here. So we know that so now we want to use the triangle ABC. So we know that sine Y, that's just equal to the hypotenuse, the opposite, which is just CB, over the hypotenuse, which is just AC. And from here, we knew that, so I can write this, so sine y, which is just CB over the hypotenuse, which is just AC. And then previously from this, we know that AC is just equal to cos x, so that means sine y is just equal to CB over cos x. So then, if we were to multiply this out, we'd just get sine y cos x, that's just equal to CB. So that's what we have over here. And then we know that angle BCE here, BCE, is the same angle as angle Y here, because it's just using parallel lines, so it's just alternate angles. So if you draw out like what the Z angle would be, like this. So that means we know angle Y here is the same as this angle here. So then we know that, therefore, the angle ECD, this angle here, that's just equal to 90 minus y. So that means that angle CED, that's just equal to 90. So therefore, that means that angle EDC is just equal to y. So that's because if this angle is 90 minus y, then if you do 180 minus 90 minus y minus 90, you just, the 90 minus 90, that's just minus 180, so that would cancel, so you just get y. So therefore, we have angle EDC here, that's just equal to y. So therefore, if we look at what the triangle CDE is, we know that the angles in that triangle must add up to 180. So now that we've figured out what angle EDC is, we can use normal trigonometry rules again to work out what the length DE is. So remember over here, we worked out that sine x plus y is just equal to DE plus CB. So we found out what the form of CB is. So now we just want to find out what DE is. So then if you do cos of y using the angle DEC, if I write that out here, so we have angle DEC, so this is ECD, we worked out this as y. So then if we do cos y, that's just equal to the adjacent over the hypotenuse, so the adjacent is just DE, and then your hypotenuse is just this, CD. And we worked out what CD was here, so that means CD is just sine x, so that's just equal to DE over sine x. And now if we were to multiply out, we would just get DE is equal to cos y sine x. So then if we just insert our expressions for DE and CB into this equation for sine x plus y, we would just get sine x plus y is equal to DE, which is just sine x cos y, plus CB, which is just cos x plus sine y. So that's how you can derive the formula for sine x plus y or sine a plus b. And if you were to just do sine a minus b, you just switch around the addition to subtraction. So it would now be sine a cos b minus cos a sine b. So that's the geometric proof again. Let me just run through it quickly, like to sum it up. So what we did is we drew two triangles, and then using the first triangle, we worked out what sine x plus y is, how we can write that out, and we said that's equal to df, and then we split that up to say that that's equal to de plus cb, using just some rules that like lengths in a rectangle are equal, and just using trigonometry. And then we, in order to find out what DE and CB is, we just did a variety of more trigonometry to try and find those out. and then once we found them out, we just plug that back in. So if you want to go through this again, it's quite complicated, so it's all on here, so just go through this a lot, and you can pause the video here, and if you just want to go through it yourself again, feel free to. But now let's move on to the cos A plus B formula and see how we could use geometrical proofs to prove that one. So in order to prove the formula for cos A plus B, which is just equal to cos A cos B minus sine A sine B, or if we want to use x and y, it's just the same thing. Cos x plus y is equal to cos x cos y minus sine x sine y. So this proof is a continuation of the proof that we had for the sine x plus y proof here, which I've just written out again, just some of the steps that we need for this. So again, we're using the same two triangles, and we're using the same diagram for the proof of cos x plus y. So using the triangle like we did before of triangle AFD, we can write that cos x plus y here, which is equal to the adjacent side, which is just AF, over 1, which is just over the hypotenuse, which is just 1. So that means that cos x plus y is just equal to AF. And then if we were to split up AF in terms of two other sides, we get, if we have AF is just equal to this whole side, AB, minus just FB. And then if you do that minus that, you'll just be left with AF here. So now we want to try and find out these two values and expressions for that, which could relate to this one. So using what we did here with equation 2, where we got that AC is equal to cos x, we can use that over here. So the next step we want to do is using the triangle ACB, we can write out that cos y is just equal to the adjacent over the hypotenuse again, and the adjacent is just AB, and the hypotenuse is just AC. So because we said that AC is equal to cos x, that would just be equal to AB over cos x. And then if we were to rearrange this and multiply cos x from both sides, we would get AB is just equal to cos x cos y. And then so the next thing we want to do is try and work out what FB is, because we've now done AB, so now we just move on to FB. So in order to obtain the length of F to B, we can obtain the length of E to C, because if you remember, like this whole E, B, C, E, F is just a rectangle, so the opposite lengths are just going to be equal. So to do that, we can show that the angle EDC here, we showed that over here, is just equal to y. So we can label that again. So that's just equal to y. And then we know that DC, that's just equal to sine x. When we said CD is equal to sine x, so CD and DC, they're just the same. So we've already shown that. So we know that this angle is y, and side DC, that's just sine x. So now if we wanted to try and work out FB, we can work out what EC would be. Is that equal? So we can, using trigonometry again, this would be a right angle triangle here. We can show that sine y, that's just equal to the opposite, which is just EC, over the hypotenuse, which is just CD. So that's just equal to EC over sine x. And then if you were to multiply sine x from both sides, you'd get that EC is equal to sine x times sine y. And that's just, as we said before, because EC is equal to FB, FB would just be equal to sine x sine y. So now that we've got this whole equation, now we've got AB, the expression for AB, and we've also got the expression for FB. So we could just plug it in here. So we just get cos x plus y is equal to AB, which is just cos x cos y, minus FB, which is just sine x sine y. So that's how you prove the addition formula for cos A plus B. So if you were to do cos A minus B, you would just substitute this minus expression for an addition, so you just do the flip side. So the geometric proof is quite complicated, similar to the sin x one. So I would just recommend you going through it again. I've written out all the steps clearly over here. So the cos x is just a continuation of the sin x plus y. So just learn both of those and the method in which you can use to prove it, so that if they ever ask you in an exam how to prove it, you'll be able to. So now if we move on to the formula for tan A plus B. So now if we move on to tan A plus B, the formula for that, again, I've written out the proof over here, just so it's super clear of what everything's doing. So the basis of this proof is just recognizing that tan x is just equal to sine x over cos x. So then if we substitute x as A plus B, we'd get here tan A plus B is just equal to sine A plus B over cos A plus B. So then we can just rewrite these expressions using our addition formulae. So that means that tan A plus B, that's just equal to sine A cos B plus sine B cos A, all over cos A cos B minus sine A sine B. Now, because our formula is written in terms of tan, we want to try and get that from here. So we can do that using, again, our definition that tan x is equal to sine x over cos x. So then we can just divide each term of our expression by cos A cos B. So then if we were to do that, we would get sine A cos B over cos A cos B plus sine B cos A over cos A cos B, all over cos A cos B over cos A cos B minus sine A sine B over cos A cos B. So now the first thing we want to do is we just want to cancel out the cos B from here. Then we'll be left with this expression. And then if we cancel out the cos A's from here, then you'll be left with this expression. And then if you cancel out this part here, if you do cos A cos B over cos A cos B, that would just be equal to 1. So you can cancel that out as well. And then you'd be left with tan A plus B is equal to sine A over cos A plus sine B over cos B, all over 1 minus sine A sine B over cos A cos B. And now, using this expression here, the definition that tan x is equal to sine x over cos x, we can just substitute all of these for tan. So we get sine A over cos A, that's just equal to tan A, sine B over cos B, that's just equal to tan B, and then we would have sine A cos A here, again, that's just tan A, sine B cos B, that's just tan B. So then we get left with tan A plus B is just equal to tan A plus tan B, all over 1 minus tan A tan B. So then this is what we get over here. So let me just write this properly. So then if we look over here, that's the same. So tan A plus B, that should equal to tan A plus tan B over 1 minus tan A tan B. And then if we were to do what tan A minus B is, you just substitute those signs, you'd get tan A minus tan B over 1 plus tan A tan B. So yeah, so that's just the proof for all 3 addition formulae. Again, you should get these in your formula booklet, so don't worry about memorizing them completely, but you may be asked to prove them, so knowing the proof would be really useful. So if you found that difficult, just make sure you go through that again slowly. So now let's move on to the actual double angle formulae. So moving on to the double angle formulae, I've written them all out here, but you need to know how to derive them from your addition formulae. So let's try that out. So for the first one of sine 2a, so we want that to be equal to 2 sine A cos A. So to do that, we just rewrite 2a, we can just rewrite that as A plus A. And then if we were to just substitute B for A, we will just get sine A cos A plus cos A sine A, and then this is the same expression added twice, so that's just equal to 2 sine A cos A. So that's for sine 2a. So now if we move on to cos 2a, so if you want to try this out for yourself, feel free to do so. So we just want to rewrite that as cos a plus a, and then if we substitute that into there, we'd get cos a minus sine a sine a. So that's just equal to cos squared a minus sine squared a. And now there are two different forms you can get. So the first one is in terms of cos squared a. So we can just use our formula that cos squared plus sine squared is just equal to 1. So if we do, that's just equal to cos squared a minus 1 minus cos squared a. So that's again using just, if you remember from last time, you can get cos squared x plus sine squared x, that's just equal to 1. So then if we simplify this further, that would just be 2 cos squared a minus 1. And then for the last bit, so if we go on to this again, so we get cos squared a minus sine squared a. So then to get 1 minus 2 sine squared a, you want to substitute cos squared a as just 1 minus sine squared a. So we get that's equal to 1 minus sine squared a minus sine squared a, and that's just equal to 1 minus 2 sine squared a. So lastly, now if we move on to tan 2a, so again, feel free to try it out for yourself. So we just want to rewrite that as tan a plus a. So then if we just plug that in, we would get tan a plus tan a over 1 minus tan a, and that's just 2 tan a over 1 minus tan squared a. So that's just an overview of all the double angle formulae, and again, you will get them in your formula booklet, but for if any reason you just want to derive them or you have to derive it for yourself, you just use the addition formulae and you should be able to get your answers. So the key for like the cos 2a one is probably the hardest, but you just got to remember your identity that cos squared x plus sine squared x is just equal to 1. So yeah, that's just an overview of double angular formulae. And now we've gone over all the theory that we wanted to cover. Let's move on to some practice questions.